Hello, I'm Dr. Ron England. This is EGN3443, Probability and Statistics for Engineers. And this is the lecture to go with Module 1. And this is just going to give you an overview. The real learning is going to occur when you start doing the real work, but this will at least get you started. What we're going to talk about today is how do you use statistics in engineering, and specifically in engineering decision making. Pointing out that yes, everything is a statistically based decision. And you're going to see why. So first, let's go right into it, and let's talk about some of the basic roles of where statistics plays inside of engineering. Well, four biggies, not the only ones, but four big ones. First one being risk assessment. We build things for the real world. Okay, for the engineers, you're building things for the real world. And the real world can include much more complex environments, such as space or underwater. Now, when you're designing from the real world, there's uncertainty in the conditions of the real world, and there's uncertainties in the things that you design. And you need to know what is the associated risks of both of those things occurring are, so that you know what the overall risk of your design is. Okay, well, a big one that you might be familiar with is good old quality control. Okay, you want to build things, but you want to know before you build and as you're manufacturing something, what type of failure rates can you expect? Nothing lasts forever. When will something fail? Because you're going to be actually requested to say, hey, what's the mean time between failure for these types of things? Another good one, okay, design optimization. Design optimization basically says, okay, we're designing, we've got different options for different design decisions, and which one gives you the best. And then I kind of really already talked about the performance prediction, because that's part of that really is in the quality control, but that's the overall performance of individual systems. Responsible for all of it. All right, so kind of examples, practical examples. Really good one, selecting the material for a part. You're going to do this a lot. If you're designing anything, you got to select what you're going to make the something out of. And realizing that different types of materials have different types of material properties, but all those properties aren't fixed quantities. You just don't go, you can go to a chart and look up what the tensile strength of a specific metal is. The reality is that that is not a fixed number. It's a distribution. That is typically the mean of the distribution. So there's a little bit more complexity. And as you get into more complex types of systems, multiple types of things have to interact, each with its own probability. So much more complex than just what most people realize. You do. You're watching this. So how do we do this? Well, one of the things that we do is we actually test individual components to see, what causes them to fail, how often do they fail, and then we try to figure out the statistical, how they model statistically, and we call this Weibull analysis. Then we try to predict how long that they're gonna last, and based on that, we make the decisions. One of the things that the decisions you make is providing a warranty. So when you get a warranty on your car, or you get a warranty on something that's very complex, it is actually based upon the statistical analysis. They're not going to warranty a car to lose money. It's just not how it works. And all of those things are statistical in nature, because there is uncertainty about each of the individual components. There's uncertainty about how you're going to drive it. Okay, you fit that statistical distribution somewhere on the range of drivers, and how you drive, you fit on that statistical distribution, you personally. So what's another very, very common thing that we do in the statistical world? And root cause analysis is one of them. And it really is a simple methodology, but it's a very powerful methodology. You identify a problem, you collect data of all the things that could be associated with that specific problem. You do statistical analysis to determine which of those different types of things that you're measuring are significant. You implement a solution, and then you go right back, implement, and you look for more problems. So root cause is getting down to what that root cause is. But the key piece is that statistical analysis, because when something large fails, it isn't cut and dried what component was the root cause of that failure. This strives to get at that root cause. So another statistical thing that you do. This is one that you're going to have a little bit of fun with, Monte Carlo simulation. So once you've got something that you know fits a specific distribution, okay, you can create data from that distribution, and you can create simulations of how those systems will behave. My favorite problem with this in the Monte Carlo simulation, which is one that I might do a lecture on, I might not, because I like it so much, is what's called the Monty Hall problem. The Monty Hall problem, and this one, it seems counterintuitive when I describe it, but when you run the simulation, you realize the truth of what is the best decision to make. In the Monty Hall problem, you're given 3 doors. Behind one of the doors is a prize. Behind 2 of the doors is something that you don't want. Now, after you select one door, you're given the option to determine whether you want to go to the other door or not. And as it turns out, or you'll be shown, here's the door. You'll make a choice. Okay, this is let me just give it to you simple. You're given a choice of 3 doors. Okay, after you make your choice, they show you one of the other 2 doors. Well, they're always going to show you, they're not going to show you the one that has the prize. They're going to show you one that doesn't have the prize. So either in your first choice, you chose the prize or you chose the bad, the good or the bad. Now, once they show you the other one, they'll give you the option to change your decision or stay with your original decision. Most people would say, well, it doesn't matter. Once they showed me that door, I mean, it's still 50-50. Okay? No, it's not. It actually is a conditional probability. Okay? Your odds go from 1 in 3 in the original decision to 1 in 2 in the second decision, but only if you change your mind. Okay? Prove it to yourself, a Monte Carlo simulation where you actually create random doors and random prizes and have the person make those decisions, do you realize that by changing your mind, it's always a better decision. One of my favorite examples, by the way. Okay, now, environmental compliance. This is one that I actually worked on personally. I did environmental compliance. This was part of my dissertation, looking at stream flows, looking at a river, and I was able to take data at individual points to see if there was a violation of regulatory standards. But I actually measured the values of certain pollutants in the water. Now, they always fit a statistical distribution. They always did. Now, based on what's going on in the real world, whether it's raining or not raining, but based on how that data varies over time, taking values of that pollutant at multiple places upstream, multiple places, allowed me to make predictions at different times. Predictions of what the values would be downstreams and whether violations would occur. Environmental compliance. And it was a complete statistical analysis. So, what kind of data are we going to work with? Well, that base data at the very bottom of this pyramid is good old physical measurements. Length, height, width, weight, mass, temperature, that stuff. Then you get into some stuff that gets a little bit more difficult to measure, like efficiency, reliability. Environmental data is used very, very heavily. I've done lots of that. And then, as an engineer, you're still responsible for the economics. If you've taken engineering econ, you know it, to understand how this actually gets into the cost associated with these types of systems too, which is, by the way, not a number. It's, again, a distribution with its own probabilities. So, first you want to understand the basic scale systems. These aren't really complex, and most people just get confused in the naming. Like the nominal scale, which is a great example. It's a categorization. It just has names. Material types, steel, carbon steel, aluminum. That's a very good example of that. Okay, ordinal scale, which is dealing with things like, one of the things which is an easy one to go with, hardness rankings. Interval and ratio scale are both numbers, and the real difference between the numbers, which are just measurements, you got to measure something, but the difference between interval and ratio scale is that interval scale doesn't really have, the zero doesn't have meaning. The zero in Fahrenheit doesn't have meaning because it can be negative, it can be positive, but in the ratio scale, the temperature is in Kelvin. Absolute zero has a definitive meaning to it. It is the zero for temperature. The zero in Celsius and Fahrenheit, even though it is in Celsius associated with the boiling point of water and the freezing point of water, it's still an arbitrary number. Okay, we're not going to really beat you up on what these are because you're just going to use them. This is really just looking at the naming. You'll know what's nominal, what's ordinal, interval, and ratio without really having to think about the name of it. So, when we measure things, well, the most common way that you probably think to measure things is just getting out there and measuring it, taking that yardstick, and you're probably not going to use a yardstick, but and measuring it, but directly measuring things. In the engineering systems nowadays, it's typically done through automated data collection, which basically means you're measuring something using a sensor at specific points in time, and that data is then collected. SCADA systems are essentially, that's a measurement system. And many times that measurement is fed directly back into the feedback to show how to change the performance of how the system does stuff. Now, you do need to know that there's actually this concept of two others that you might not think about all the time. One of which is indirect measures, where you may be measuring something, but you're measuring that from a measurement of something else, which is either going to be read off of maybe a table or read off a series of calculations to get to the value that you're measuring. And then simulated, which is where you actually generate all the data for those measurements. You're measuring stuff from data that you actually created that data yourself through simulation. Now, here's something that is really important. You got to understand this to understand all of statistics. Population and samples. Very rarely do you know the actual numbers of a full population, because it meant that you measured everything. What you might have, and what you will almost always have, is a sample. But from the sample, you want to know the actual values many times of the population. Well, that's what statistics is all about, getting from the sample to the population. But here's the thing. You measure a sample. You estimate the population. You go out and measure a sample of the exact same thing, and you might get different parameters for the population, but hopefully they fit within confidence of each other. If they don't fit within confidence of each other, it means that something's wrong with your sampling. Okay? Which actually is one of the questions that you need to be able to answer in statistics. Are your samples actually valid? All right, well, what do? There's a lot of different, and this is really just examples, because almost everything is sampling. But understanding how to get good samples that are statistically significant and that can be used for estimation of things like populations is really important. So that's a little bit about what we're gonna be doing and talking about as we go through this. Now, parameters versus statistics. Again, we're getting into naming, but the difference in the naming we use different things for different symbols for the parameters that we're doing. So really, we're really thinking is what's the difference between the sample, the statistics of the sample, and the parameters, the actual population. So as you look into the notation of this, you'll see that sometimes we use mu and sigma for mean and standard deviation, and sometimes we use x bar and s. And you're like, man, they're confusing this by using different symbols for this. No, we're not. Mu and sigma are typically taken as the parameter, the parameters that are the estimated parameters for the population. Okay? Whereas x bar and s are used for the sample. Well, that's simple. So, okay, the parameters are used to describe the population, and the statistics, those individual statistics, which have their own symbols, are the estimates that go with to get that population. Put your head on the difference between a sample and a population, and that you don't really ever know the statistics of the population. You're always estimating them, and you're always estimating from what you've measured for the sample. I hopefully, and if you're having trouble with that, just rewind and listen to that again. That should make sense to you and must make sense to you, because that's the whole reason for statistics. All right, now a little bit about Python. You are, in this class, going to be using Python. You should have had at least a class in Python. If you haven't, you're going to be playing a lot of catch up. However, I also expect you to use AI to generate a lot of the Python code that you need to do. I don't expect you to sit down and try to hack out all the code. I do expect you, when using AI to generate the code, to be able to go through the code and make sure it did it correctly. Okay? It's not a matter of not knowing what the code does. It's just a matter of not having to sit down and memorize the names of all the different types of functions in the statistical libraries to do the things that you want to do. You do need to know, if you're using Python and you're asking an AI to create a statistical analysis for you, that is actually doing the right statistical analysis for what you're trying to actually measure, predict, or do. That is 99% of what you need to do. You need to know this distribution is appropriate for this scenario, and it was done correctly in my Python code, and it's visualized in such a way that it has meaning. And what I mean by visualizing is I mean plots. Okay, and there's a lot of different types of plots to visualize how the data works. You need to be able to look at those visualizations and say, this makes sense. This follows the data. This describes what I'm trying to say with my statistical analysis. Now, there are two statistical programs that are important, very important. And some people, you might use a commercial one like Minitab or something like that, but we use R and Python. They're both free, they're both open source, they're both used by thousands and thousands of scientists and engineers. And if you don't know R, don't worry. Because if you know Python, you can use RP2, which is the R library for Python, to do what you want to do. Now, if you look at all the problems, the sample problems that I gave you, I've solved them both in R and in Python. And they are both runnable inside of R and Python. But because R has a module that allows you to run R code inside of Python, there's nothing you can't do. There's nothing that you can't do in Python that's only available in R. Now, both R and Python do give you some incredible visualization and graphics. And if you're using AI, and I don't expect you to be at this level of programming, but you can ask the AI to create the visualization tools that are actually interactive, that you can run, that give you dashboards and things like that. Okay, and if you know Python, you know how to implement those things. Okay, because in a lot of the cases of the problems that you're going to see, that visualization capability is going to be important. Visualization is key. Now, much of the times you're just basically going to create plots, and they need to be good plots, and they need to have everything on them to actually correctly visualize the problem itself. But you know what? Once you know what you want on the plot, you can go right to an AI and ask it to create the code to do this. You can say, here's the data that I want you to build it with. And if you want it to be an interactive visualization, if you write the code to say make it interactive, it will likely do that for you, and you can do that, and you can get that code back. Not only that, but a lot of times you can actually have it do that inside of things like JavaScript for implementation inside of web pages. I do that all the time. Okay, I actually say, someone says, can you make this actually available to you on a website? And I can say, I sure enough can. But I don't sit down and write all that code. I know what kind of visualization tools I want to use, and I know I want to do it in JavaScript so it works inside of a web page. You're not going to do that in this class. This is all going to be done in Python, but I want you to have an awareness of R, what R does, and how it actually is the most robust statistical library available to you. But it's also a relatively complex programming language. Python's a complex programming language. The beauty of Python is it's also a simple programming language. So, bottom line, statistics are used in engineering. You need to know statistics. The reason for this class is so that you know the statistics with direct applications of how they work in engineering, because I've done tons of stuff. I mean, I've had classes after classes in statistics so that I can do very, very complicated analysis. We're not going to go into that level of depth. We're going to solve the stuff that most people do most of the time. But in the real world, in the engineering world, you need to make decisions based on real evidence and real data. You need to understand that everything has a level of uncertainty. You need to know how to use the tools to do all the stuff that you want to do inside the statistical world. And you need to learn to be efficient, which basically means you shouldn't have to go out and do massive amounts of testing, because if you understand the statistics, you can actually optimize even that piece. So I hope that you enjoyed this. I hope that this was a useful lecture to you. And we're going to get down into the actual nitty-gritty in the very next lecture, even though we're going to start with some simple stuff. It's going to get into some healthy statistics pretty quickly. Thank you very much. This is Dr. E signing out.